analysis. In fact, this is the video. It's about how to reduce the effect of problems structurally and non-structurally that could happen in any earthquake. But why we choose this topic? Because the rate of existing a few earthquakes become accelerated. By days, we can listen or we can see that earthquake happen in such country or that. So how to reduce this problem? If we don't study it, what was the problem and what can be the solution on both way as a structural and non-structural, starting by small video about it to share it. I will share which one. Okay. Can you see it? Can you see my screen?
Yes, sir.
Okay. So those are, in this small ones, those are the main parts that we are going to check it. Some definitions about what are the structural element, what are the problems that could happen to structural element. In fact, I choose the earthquake that hit Turkey in the last year, since there is a lot of videos and photos taken by several scientists. So, and after that, I will check what are the solutions. We have many solutions. The problem is not the code. The problem to understand what are the limits in the code, what will happen if we, by mistake or in economic factor, I say, no, I will not put this because it will cost more. So what will happen and what are the solutions on both ways, as a structural one and non-structural. For example, I will discuss about the P delta effect. This is a real photo taken by one of my friends there. He told me, sir, you can see that the building from the bottom way still fixed, but at the top there is like someone pushed it a few meters. So what is this P delta effect and how to reduce it? In addition, we'll talk about a patent that got by one of the scientists. It's about the hairpin shape reinforcement, how to make the connection more resistant by using this type, the hairpin reinforcement. I registered one patent and he registered another one. I have more than 10 topics that discuss about the benefit from using this main element. Regarding this one, recommended by several codes. After that, I will discuss about the causality and cause and continuity concerning the non-structural element. And we refer the National Center for Seismology, NCS, follow it in your countries. We have other codes that we can also suggest it as ACI code. Those could be the main elements that we can discuss about it. What do you think that we can search about this? Why? Because you are saving our life. We can saving the life of the others. I always say during an earthquake, when the building falling down, what happened? Is this a fault of construction or a fault of design, of supervision? Sometimes you have all this effect together. So this is could be an introduction for our future session, and hope that we can share our knowledge to benefit from this one. Thanks for your attendance.
Can you show the video, Dr. Khatib?
Uh, yes, I show it. You cannot see this small video.
No, that video was not projecting. So you'll have to just change the screen to that once you start the video.
Okay. Is it visible for you?
No, just press Alt Tab.
Oh, come on.
So you can share full screen. Uh, then I think you will be able to share.
Can you see it now?
Video is not visible. Your screen is visible. That is your, I
Methods
think,
to reduce the damage is not visible for you, sir?
no.
Oh, come on.
Or you can upload it in the WhatsApp to me. I'll try to share. So by the time we are getting that video, all can discuss with me what problems if you have faced while design of the shear wall. We will cover it during the session. So any query points are there which should I address for the shear wall design, dual system design? Hello. So we have Ratnesh, Ravi, Abhishek, Swapnil, Chetan, Vikas and Anand. So anybody can speak if you have any query in design of shear wall or dual system. Okay, let me start with the session. So good morning to all and happy Makar Sankranti to all. And I'll start with the design of shear wall, and it is IS13920 2016 that I'm referring. And The part covered in this code is a rectangular shear wall, whereas we are using mostly the plain shear wall for design of the core, that is C type, T type, L type, F type. So various different arrangements we have. Yeah, Mr. Ravi, you have any point to speak? Hello, Ravi. Am I audible? Hello, am I audible?
Yes, sir.
Yeah, yeah. So Ravi, any query point? You have raised your hand. Okay, you can also type in your queries if you want. Okay, I'll just from the chat box I'll take the query points. So this is what we are having in IS13920 is a rectangular shear wall, but what we prefer in this what we say that routine design, the plain shear walls as well. So Indian code does not have that plain shear wall design. For that we should refer ACI 318 and specific reference book of Dr. Jack Moyle. That is the latest one, and if you want to use the previous one, that is by Nigel Priestley, so that will help you to design the shear wall with flanges. So the formula is mentioned in the book of uh, Jack Moyle. So we are starting with design of the shear walls. So spatial shear wall, and it is also called the structural wall. Okay, so it is a vertically oriented planar element. So this is very important. We start with the definition of shear wall. Shear wall is there always to resist the shear forces, that are the lateral forces of the earthquake. Okay, and it also can take the axial force as well as the bending moment, but in which direction it will take, that is very critical. It is in its own plane, that is out of plane it is not going to take the forces. So if I can draw this particular behavior of the shear wall, then if this is the wall and forces are in this direction, this will be the axial force, lateral force, axial force, and there will be a moment onto the wall. So all are in plane. Okay, so they are asking the shear wall to resist in this particular direction only. Okay, so out of plane would have been that you are resisting in this particular direction. So shear wall is not made for resisting out of plane, but if the out of plane forces are getting generated in the shear wall, that is what you need to check. So it may fail out of plane if the out of plane forces are getting generated. So you have to make sure that out of plane forces, if they are getting generated, that also should be taken care. Otherwise it will lead to failure. By but general definition it is not taking out of plane, so check for out of plane action. So it is designed for in plane only. I hope you have remembered the lecture of mechanics in which in plane out of plane action is generally taught. So in plane is along the major direction. So major direction of resistance is along the length of the shear wall, not along the width of the shear wall. The cross section size in the along the width is very small, so resistance will be very less in out of plane action. So for that we are not designing, but if the out of plane action is existing, you need to also consider in design. Otherwise you don't have to consider out of plane action in design. And in reality, earthquake, some out of plane action generally happens in the shear wall. Okay, so for that we are not generally considering, but if the amount is more, the shear wall will fail in out of plane action. Okay, so that's why we have arrangement of shear wall whenever we are planning. What we are doing, that shear wall we are planning on this side also, we are planning on this side, and also in this but two directions. So if the orientation of shear wall is very less in this particular direction, okay, then the force may redistribute to the walls in between, that is out of plane. If the in this direction the amount of shear wall or the resistance of the shear wall is more, then lesser force will get distributed to these walls and the columns. So how much force is getting distributed in this direction in the shear wall, how much force is getting distributed in this direction for the shear wall, because in this x direction this wall is going to be under minor axis, the forces will be under minor axis, that is out of plane, and this direction was, so this is y and this is x. Then you need to orient your walls in such a way that your 100% forces are taken by the walls in that particular direction in which you are assigned the oriented the shear walls. And the second category would be that we are having the core. So there is a core in center, so it may be a double core or a single core like this in one direction, and we may have a different set of walls in the other direction, but I have seen only central core, and all are the columns in the perimeter and all those things. So that is not suggested because it will give first mode as torsion. So keeping only the core wall, you need to check for torsion. Otherwise you have to have very good density of this wall. Okay, thickness of this wall, basically the density has to be so much that it does not cause the torsion as the first mode. And for that you will have to connect it with the perimeter elements. So whatever the columns are there at the perimeter, you have to connect with them properly. So it will be a core connected with the perimeter. Okay. So this way you need to arrange your building with, if there is only a central core should have very good density and it should be connected with the perimeter. So perimeter will also take part in lateral load resistance, and in between columns will not take part in the lateral load resistance. So that would be defined as the gravity columns. So that also needs to be checked and proved that 100% forces are getting redistributed on the perimeter, and the connected elements will transfer the forces from core wall to the perimeter. So perimeter and core wall has to be adequately uh, connected so that the first mode is not your torsion, and also the torsion does not dominate the design of the building. So that would be for the C type of this is C type of the shear wall. Okay, this is C type. Then there is L type, then there is T type, then there is F type. All type of walls are arrangements are provided in our buildings. Okay, so here there will be a lift, single lift is there here, two side lift is there, here is a single lift in this core, and if you connect it more, then that way it will keep on adding. So in L also shear wall, you would be having some or the other requirement. So there are two ways. There is a staircase well. Generally, it is near to the core of the building. So if this is the lift well connected with the core, so that also should be inside the shear wall. So your staircase should be covered with the shear wall as per the requirement of the code. So your staircase cannot be without shear wall. It should be enclosed within the shear wall, and it should have good earthquake resistance generated due to the presence of the shear wall. So that is why the uh, lift core and the staircase well. So your lift well and the staircase well should be within the core of the building. Okay, otherwise it will not suffice the requirement. You will have to separate it out then. Staircase with the core wall if it is not connected. But as per the requirement of the code, it should be have three sides of the shear wall. So I would like to know from the people in the right now, the participants, that are we doing that or not right now? Are we connecting the lift well, sorry, our staircase well with the shear walls? Our stair well, are we connecting it with the shear wall or not? Or it is surrounded by shear wall or not? Or we are keeping it unprotected?
No, sir, we are not connecting in our projects. It's unprotected.
So what is the code requirement basically? Anywhere it is mentioned that we should protect it.
N- No, sir, we did not find any that clause actually. But what you told is right. If it is unprotected to the boundary of the periphery, then mostly it will getting torsion in the second mode.
Hmm.
Yeah, sometimes first mode. But again, we are doing some jugaad, just like removing the shear walls or increasing the shear walls, and we are checking the center of mass, center of rigidity, and we are making it to the third mode. Sometimes we are not making it to third mode also.
Mhm.
But we did not find any clause that to give connectivity to the periphery.
There is no such clause to give connectivity to the periphery, but that is one type of arrangement that is done if the first mode is torsion. If the first mode is not torsion, then you will keep just the core. But if the first mode becomes torsion, then you need to check that how much force is taken by the core wall, how much force is taken by the frame, and what arrangement you have done. It needs to be thoroughly checked if it is
Yes,
just the central core.
yes, sir. That's right. That's right.
And unprotecting the stairwell, what will happen that under earthquake, during the earthquake, the staircase will fail. We will not be able to use the staircases, and also we will not be able to use the lift well. So during the earthquake, we cannot use the lift. We have to use the staircases, and if they are not protected, most of the fatalities happen due to that, because people rush to the staircase and it is not having that earthquake resistance. So if
Okay.
force gets transferred to that part of the building, and if it is failing, then it will lead to fatal, large number of fatalities. So that's why
So
it should always be protected.
okay, you are saying that we have to look into the diaphragm forces.
Yeah, so if you have connected the diaphragm
Sir.
and it is getting transferred to the columns of the lift, your stairwell,
Okay, sir.
so your stairwell will be vulnerable to the earthquake forces, right? If you have not uh, protected the stairwell with the shear walls. Okay, so column will be experiencing that shear force. Though you have connected the core of the building, So your 100% force, you are assuming that the earthquake force will be taken by the central core wall. But if the it is not happening that way and shear force gets transferred to the stairwell, then people that are going to use the stairwell will face severe means what we call injuries or fatalities if the stairwell is failing under the earthquake. So it should be protected for the earthquake action. That is what is one precaution we can take if we are having stairwell separated from the core wall. Otherwise, you can include the core wall in which the lift well as well as the staircase are protected in one particular arrangement. So you can reduce the vulnerability of the staircases to earthquake, because during the earthquake we cannot use the lift. So there is only one way out, that is the staircases and the fire exit. So people may use fire exit or people may use the routine staircase during the earthquake. So that should be protected with shear walls on three sides.
Okay, sir. Okay.
So right now we have the arrangement in many cases that open staircases are there, so that it looks good. But if open staircases are there, it should not be vulnerable to earthquake forces.
Okay, sir. But whatever the thing in for earthquake, the staircase we are not designed for earthquake, right?
If it is going to take the forces, okay, you need to check whether the vulnerability is there or not,
Okay, okay,
because you have not connected it with the shear wall, okay, and the columns that are supporting the uh, there's a stairwell, okay, they are now the gravity columns, because they may not take the shear force if shear force is not coming. If shear force is coming, we should protect it adequately in that manner. So protection of staircase is important, and enclosing it with the wall will help us to avoid that. But it is a solid wall from top to bottom, so we don't have flexibility of any opening or that way in other directions. That's why people keep it separated from architectural point of view, but from structural point of view, it should be protected.
okay, sir.
So you have to give heavy columns, or that way some amount of forces you should consider that is going to come on the minimum nominal forces, like 25% we have for the dual system, right? So our frame takes 25%, so you at least assume 25% will come on the staircase and design your column accordingly. Then also it can help. So some way or the other way, we should try to reinforce our staircase area so that people can use it during the earthquake, and most of the fatalities happen when the people are trying to escape. Rather than if you take a shelter inside the building, you may survive, but if you are using the vulnerable staircases, very difficult to survive after during the earthquake or after the earthquake. So that was one in a particular set of information, types of walls, and what is a shear wall basically. That is in plane action. If there is some out of plane, you should consider. And all these walls are not given in the IS code. Okay, we just have the rectangular shear wall given in the IS code. So we need to refer ACI 318 for its design, and the reference book by Jack Moyle for its design. Okay. This is as per the IS code. This is not showing rectangle. Let me draw. So this is rectangular shear wall that we are having in IS 13920, and that is what we are going to discuss.
Sir, and in this session, you also mentioned that please how to read this in plane moment forces. Actually, in E-tabs, we have a column that in plane moment or peer forces to see the moments. But Right now, I am using the SAP. I am not getting how to check this in plane moments. Could you kindly address this topic too?
SAP 2000.
Yes, sir. Yes.
Okay, so
There is nothing, any option like to read it in plane moments. If we, there is only things we are assigned as a wall as a shell element.
hmm,
So we are collecting the F22 forces. We have that. But how could I read that in plane moment forces? Where to check that? Or else I can only check with stresses.
I think SAP 2000 is not having that feature because it is purely finite element software,
Yes, sir.
and it by default divides the element in small pieces. And let me
In
check the restraint if you provide na, so your moment will be generated on the restraint portion, that is on the reaction that we get.
yes, sir. In one of the articles somewhere, I mean, in the browse in the net, I find one of the article. Just like the scenario, what he told, the in-plane moment forces will include in the F22 forces.
Yeah, yeah,
So you don't worry about that in plane. It's there
yeah,
is no
yeah.
option to see that.
Yes, yes.
If you really want to struggle for those things, means you go for S11, S12 stresses, and you look into that.
Yeah, basically it is only the stress value, stress contour you will see. You will not get the reactions. That's why we are not using SAP 2000 mostly for design of shear wall, but for research purpose we use SAP 2000 because it
Sir.
gives accurate FEM results. And ETAPS is also developed in that same company software, but it has a different output as compared to SAP 2000. So it purely works on FEM. So F11, F22. Then your that is in your x direction the shear force and moment, y direction shear force moment, z direction that is 6 degree of freedom, and also I think it has warping forces also. So 9 degree of freedom SAP 2000 has. E types has 6 degree of freedom. Okay, so that is if you are designing the steel elements in SAP 2000, you will have 9 degree of freedom as compared to any other software.
Okay.
Okay, so it is purely following the FEM rules. So based on that, how you are doing analysis in FEM or design in FEM, same you will have to follow here. So you get stress strain as the end of the FEM analysis. So that is what it is showing you, the stress and strain.
Okay, sir. Okay.
So that is the reason we use it mostly for research purpose.
Okay. Got it.
Yeah. Thanks for the question.
Thank you, sir.
So basically, it is a plane element. I hope you know what is a plane element. It is a plane element. It goes back to the mechanics part. That plane section remains plane before and after bending and all those assumptions that we take. So it is a plane element. But what we assign it is a shell. Okay. So vertically oriented planar element because it is a plane surface which has lesser thickness, and it has to be assigned as a shell element. So the design will change because so what is the difference between plane element and shell element? So can anybody tell the difference of plane and shell? What changes while we are analyzing a plane element versus a shell element?
Shell element will have both in plane moments and out of plane moments also. It's will resist.
Uh, in plane and out of plane.
Yes.
And plane elements will have what?
I mean, shell can take the uh, how could I say that?
Sir, Kyle.
Sorry. Hello.
Sir, can you repeat the question once again, please?
So what would be the difference between shell element and plate element?
Plate element does not show any out of plane bending, sir. It can resist only in plane moments only. I mean, just like wind or earthquake forces.
Mm-hmm.
But shell as a both, it can resist both in plane and out of plane. I
So
mean, in the
membrane elements can support in plane, right? Membrane, like what we are designing as per IS 456-2000, the slabs. Okay, so they are designed as a membrane. So membrane element does not take any forces.
out of plane.
Okay,
Yes, sir.
takes only in plane forces, and
Yes.
it does not participate in any resistance. So full force goes to the perimeter beams on which it is connected. Okay, so the beam design will have higher moment as compared to the real moments, because actually the slab participates uh, in its moments in membrane case. So that would be a membrane element that is bending. I think slab bends out of plane, right?
Yes, sir.
So out of plane, we have the membrane element. Plate element also can bend out of plane, or is it in plane?
In plane, sir. Out
In
of plane
plane.
moments are very less to those things. Plate
Yeah.
mostly for the in plane.
Yes.
Am I right, sir? I
It's the
Yeah,
plate
yeah.
element also takes the out of plane moment. No? So plate is in bending. So when anything is bending, it will be out of plane,
Okay.
right?
Right, sir. Right.
And your shell is combination of plate and membrane.
Yes, sir. Yes.
So it is in plane, out of plane, both it will take.
Right, sir.
So that is it is a basically a 3D object. Your plate and membrane is a 2D object. So 2D object, they are mostly governed by bending. Here the shear force is also a major part of it. That's why we are when we are designing for shear wall, we are calling it as a shell element, because we consider the shear forces also as a major part in design. So when we are talking about membrane, we are talking about bending. When we are talking about plate, also we are talking about the bending. Bending is the major resistance required, whereas in shell, your shear action is also dominating.
Sir,
So it
I
is
have
a
a question that let us suppose if I keep my wall as a plate and if I draw the wall in ETAPS as a plate, then what is the major change in the analysis
plate
where I
takes a bending only. Bending as
okay,
the
sir.
major criteria. Shear is not taken care as the major criteria. So that's
Oh,
2D element versus the 3D element.
okay, sir. So you are saying that in the analysis the shear forces are I will get very less forces, right?
Mm,
Or
shear
else it will
forces.
fail in the shear.
So you take a plate that is going vertically, right?
Right, sir. Right.
Now plate has a 2D element that is not in the third direction.
Yes, sir. Yes.
So you applied the literal force to the plate, let's say.
Okay, sir.
So that plate also will bend in that direction, right? So moment has to get generated
Yes.
versus the shear that has to get generated. So your estimation for shear will not be correct.
Okay, okay. So it will show the forces, but the
Yeah,
forces are pseudo forces.
yeah, because it is a 2D element, you
Right,
require
sir.
a 3D element.
Right, right. Got it,
So
sir.
when we are doing with steel plate shear walls, okay, so in steel everything is a plate,
Right,
right? So how would you assign plate as a shell element? That is not possible if you are doing with steel building.
right, sir.
So in that case, you would be assigning it as a plate. But when you are dealing with the concrete element, you have to define it as a shell element, right?
Right.
So shear is more dominating. For shear walls, steel plate shear walls that we say, it is made up of plates but dominating in shear forces. So while definition, you have to make sure that what you are defining has to obey the requirements.
Right. Right. Right.
Okay, so going
Yes.
ahead, thanks. So it is a basically a shell element which takes the axial force, shear force, and bending moment in its own plane, not out of plane, that I explained with that particular sketch. It is a structure, and if we are going for a spatial shear wall, it is a structural wall meeting spatial detailing requirements for ductile behavior. So you have to design it as per the section 10 of this code, which will take part in lateral load resistance in the earthquake, and you will get a particular R value related to that if it is a ductile wall or it is a ordinary wall. So difference between ductile wall and ordinary wall is the ductile detailing. If you are following section 10, you are designing spatial shear wall. Otherwise, you are designing ordinary shear wall. The ordinary shear wall, the uh, your spacing of the stirrups, that is the horizontal reinforcement, will be different, and your horizontal reinforcement as per section 10 will be different. So you need to first categorize what wall you are using, that is spatial wall or ordinary wall. So design will change. The mechanism will be the same, but your design will change. In that particular case, your R value will change. As it is not ductile, your R value will become less.
Sir, I have a question in this area. Sir, can I say that non-structural wall is a normal shear wall? Hello.
It is a structural wall, but it is ordinary or ductile. That is the case. Non-structural wall we are not considering as anything.
Okay, sir. Okay.
If it is made up of bricks, okay, then we can consider the density 21 or 20 versus the 25. So it will have some shear resistance, but it does not have any reinforcement, so no ductility.
No, 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 sir. Non-structural with the RCC, but in the model we are not consider that.
But once you have declared it as a non-structural, okay,
Yeah.
that means it does not have the capacity to take the forces.
Right, right.
So that we don't consider its participation then. If it is to be considered in participation, it has to be declared structural or non-structural.
Okay, sir.
So we need to protect non-structural elements while we need to design structural elements. So that is the difference between two, that if non-structural elements are getting some forces, so we design non-structural elements for those forces, and either we separate it out from the main frame. And if they're participating in lateral load resistance, we declare as structural because they will also transfer the forces. So we cannot break them after its construction
Right, sir.
because they will participate in resistance or under redundancy action.
Yes, yes.
So frame versus shear wall we have discussed. We will go to section number 10 of 13920 2016. So our if you are designing as per this particular clauses, then you can declare it as a spatial shear wall, otherwise it is a ordinary shear wall, and your detailing standards will differ. It will be non-ductile, this is ductile. That's why your R factor will change. For R factor, you need to refer IS 1893. So minimum thickness of special shear walls shall not be less than 150 mm. Practically 175 or 200 mm you would require. Otherwise, if you refer the book of Jack Moyle, 150 mm also is not good enough as a special shear wall. Also, your concreting will not be good enough. You will face difficulty in concreting if the thickness is 150 mm and declared as a ductile element. Your reinforcement congestion will become high. So at least 175 to 200 mm is recommended if you are considering as a special shear wall. And also your dia of the bar, if it is you consider something with respect to dia, the thickness, then also you need to check, because in the column it is given. So first you need to check whether my element is a column or whether it is a shear wall. So that is the first check you need to do, and based on that you can decide for the reinforcement and thickness of the wall. So minimum is given 300 mm for buildings with coupled shear wall in any seismic zone. So if it is a coupled shear wall, coupled, that means two shear walls are connected by coupling beam in between. Okay, so that has a good energy dissipation, because the coupling beams will act as a fuse and they will fail uh, during the earthquake, and that is a major earthquake, it will fail, and energy dissipation will take place on the higher scale as two walls are connected with the coupling beam. So if that is the case, if it is a coupling beam, minimum thickness of the wall has to be 300 mm. So also, as per the fire resistance requirement based on occupancy given in IS 456-2000, minimum thickness of the wall has to be decided. So fire requirement and two of these requirements will define the minimum thickness of your shear wall, special shear wall. And if it is a shear wall or whether it is a column is defined by the ratio of the length of the wall to its thickness. Okay, has to be minimum, very important, is minimum 4. That means your L, length upon thickness T of the wall, should be greater than or equal to 4, right? That is the aspect ratio of the wall. Let's say we are talking about per story, and our wall is generally from top to bottom. So should we consider the shear wall from roof to bottom, that is your length versus the thickness, or should we consider floor to floor, this aspect that has not been mentioned here? So what is that to be followed from top of the building to bottom? That is your height versus your length. What is the length of the wall at the bottom? So length has to be constant, right? It does not vary with height of the building. It is a length at the base of the building versus its thickness. So is it length we are talking or height we are talking here? So it is clearly mentioned the length of the wall to its thickness, not the height of the wall to its thickness, right? So we should be clear that length of wall in plan versus its thickness, the ratio should be greater than or equal to 4. So what does it mean basically? If it is not greater than or equal to 4, then your thickness is more and your length is lesser, then only it will reduce. So thickness increases, denominator increases, then it will reduce than the 4 value. So width is increasing, and in that case it will become a column. In a particular case, from one particular ratio it will start becoming a column, and one particular ratio it will start becoming a shear wall. Okay, so based on length versus thickness, you should assign whether it is a wall or whether it is a column. So wall versus column, the basic differentiation you can do with this particular aspect ratio. And second way to do it is by your bending moment diagram, SFT BMD diagram. You can easily understand whether it is a shear wall or whether it is a column. when we are designing a column, you would observe that your bending moment diagram is like this, right? That is story 1, story 2, story 3, let's say, and it continues up to any number of story. So it will have positive and negative bending moment like this. Whereas when we see for the shear wall, it will be something, bending moment diagram will be something like this. Okay, so this would define it as the shear wall and this would define it as the column. Okay, so that is the basic differentiation you can make based on the bending moment diagram, shear force diagram, and your aspect ratio. So two ways you can check whether it is a column or whether it is a shear wall. So shear wall continues from terrace right up to the top of the raft of the footing. It is continuous, whereas column is story wise. Okay, so this is the ultimate moment, that is total moment, not ultimate moment, let's say it is a total moment at the base.
Sir, I have a question in this area. Sir, many times I'm seeing that let us suppose I have a column of 1500 by 400 something. When we are checking, let us suppose I assign my column as a frame element. I'm checking my story stiffness. Suppose it's not satisfied means now I'm removing the column as a frame element and assigning the column as a shell element. I'm analyzing. Then many times the stiffness criteria is going to be set. I'm not understanding really what happening for the stiffness. Whether why it's not satisfying the frame element the stiffness, why it's satisfying the shell element for the stiffness. So what is the internal extra feature is adding to the shell element?
Yeah, shell element is more rigid, na, because it is a 3D element.
Okay. So I mean, sir, which one is the real scenario to understand this stiffness criteria also, whether shell or frame?
So if it is a shell element versus a frame element will go under bending and your frame element will be story wise. Your shell element, if you have defined it as a story wise or as a continuous element.
The shell as a story wise only, sir.
Okay, so I would suggest you, because direct answer is not there, you will have to yeah, Dr. Miller, you want to say something?
Yes, concerning the question, usually when we use as a column, the system during analyzing will consider that there is some redundancy in the column, which is mean the hinge, the end support of the column will become like a hinge. Those hinge does not support and cannot support a moment. Furthermore, when I will consider this element, the column meanwhile, as a frame member, now this frame member will can support moment, so it become more resistible. Is that clear?
Hello, is
Hello, can you hear
answer.
me?
Yeah, I'm just asking the person who asked the question.
Yes, sir.
This
Yeah,
is
I'm hearing. I'm listening, sir.
Okay, thanks.
Sir, and one more thing is in 10.1.2 clause B, 300 mm for building with coupled shear walls in any seismic zone. Sir, how could I encounter that whether my shear walls is behaving like a couple? Let us suppose I have a two walls with a connectivity beam of 250 with a small depth. Can I ensure that the entire system is getting a coupled, or else the depth should be sufficient for what? How could I encounter that whether my shear walls are coupling beam? coupling. I mean, I want to ask any specific depth to get the coupling action.
Yeah, just hold on. We'll reach there. Uh, just looking at that coupling beam requirement.
Or else just like our deep beam 2.5 to.
Yeah, basically it is also a 3D element, coupling beams. Yeah, I could see this. Now, coplanar spatial structural walls may be connected by means of coupling beams. If the earthquake-induced shear force in the coupling beam exceeds this, the definition of the coupling beam is not given in our code. Let me check at the beginning if they have defined the coupling beam. I don't think they have defined the coupling beam in our code.
Yes, sir. There is no anything that. But
Hmm.
I'm seeing that many people are connecting the beam with 300 depth also. They are saying that it's a coupling behavior.
See,
I
it
don't
is
think so.
dominated by shear, not by bending. So, simple arrangement is if your beam is dominated in bending, then it is not a coupling beam. It has to be dominated by shear. Design has to be shear dominated. Your size has to be of such amount that bending will not cause as a failure. It is mostly shear governed action. So that is the reason, let's say, I asked to refer you the book of Jack Moyle.
Yes,
I
yes.
don't remember exact page for this. And currently,
So, sir, you are saying just a value. Let us suppose my shear force value is 500 kilonewton. My bending momentum is 250 kilonewton per meter. So it's a governing of shear force. So it's we called as a coupling.
so your deep beam is basically dominated by shear, right?
Yes, sir. Yes.
So that is the way it should be considered.
Okay, sir. Okay.
So you can consider it as a deep beam. Mm, I'll have to search that section of this book where it is exactly given. That I'll share later because
Okay,
I'll
sir.
have to see in this where it
Sure,
is
sir.
mentioned. What was so the coupling beam? Okay, I can see it here if I'm able to see that page. I think this is the one in which it is not visible. So I'll open the other, but here also in this book also of Nigel Priestley, you will find coupling beam, but I'll share it separately. Right now, I'll not be able to locate it exactly. Okay, so I'll share what is a coupling beam, but it is shear dominated. It is also a 3D element, shell element, not a plane element. So plane element are dominated by bending, designed for bending action mostly. Here it is dominated by shear. Okay, so that's why we are having the diagonal reinforcement are suggested for coupling beam to take the shear forces, right?
Okay, sir.
So that we will consider it as a mostly a deep beam with shell element properties. Okay, so moving ahead, what is the definition of the wall and what is the definition of the column? Okay, how to define it by aspect ratio and by behavior that I explained. Now the squat wall that are very shorter walls that is larger length. Yeah. Yes, sir. You can speak.
Concerning the coupling beam, if I have uh, two different elements structurally, like the shear wall that you talk about it, and I need to connect them. So this element laterally one, connected them, we call it the coupling beam. At the first, those two shear elements, shear walls, each one have its own behavior and work separately. Once I add this shear elements, this shear beam, this coupling beam, now I will have the all behavior to work together and become more deep one, more functional one. Okay?
Yeah, yeah.
Okay.
So it is also a shear beam, as he said. Okay, so it is a coupling beam, mostly a beam governed by shear and not by flexure. So its size has to be that way. You cannot assign a 300 size beam and call it as a coupling beam, because it will not resist uh, or not transfer that forces. Okay, so it should act as a fuse element between the two shear walls, then only it will have higher energy dissipation. Otherwise, the two shear walls will work separately and the beam will fail with very less force under bending rather than shear. So shear will come, that beam will fail immediately. So defining it very small 300 size beam with respect to its span, we need to check the depth and the span of that beam before defining it as a coupling beam. And software should also show the error, but I don't think software will show the error if it is not defined correctly. So structural engineer has to be really be informed about a coupling beam, how it is to be defined, how it is to be detailed. And for that you should refer the book of Jack Moyle in this particular case.
Okay, sir, got it.
Yeah, thank you. So height of the wall versus length of the wall, it is less than 1, that means your height is less, so it is acting as squat wall. So short wall and length is more, so it will act as a squat wall. Intermediate, so height versus the length, 1 to 2, then it is intermediate wall. Slender walls is height to length greater than 2, so height is more, your length is less. So that is the general case we come across whenever we are dealing with high-rise buildings, or mostly any multi-story building more than 3 stories, then we will not get squat walls. And intermediate walls also up to some, let's say 4 or 5 stories we may get, but beyond that all will be the slender walls that we would be designing. And that's why 13920 also has given the design of only slender walls. So they have not given design of intermediate walls and squat walls. But if you refer the book of Moyle, he has given the design for all three type of walls that you may come across. So we would be dealing with design of the slender walls in this particular case, as per our IS code. So in the design of the flange wall section, now we are moving towards the flange wall. Only that part of the flange shall be considered which extends beyond the face of the web of the structural wall at a distance of at least equal to or smaller of. So how much of the flange to consider? Now this is my, let me draw a T wall. Okay, now how much effective width has to be considered for the flange? So this is the web and this is the flange. So as you know, flange takes the bending, web takes the shear. That is how the flange shear walls also work. And how much be effective we have to take. Either we need to take the full width of the flange as capital B, or how much is the length we should consider for participation in the forces, resistance or the design. So that criteria has been given in the code. So either it is actual available width, full capital B, full width of the flange we will take, or half the distance to the adjacent structural wall web. So if there is a wall nearby, if I say that these are the two webs are there, so half the distance between the two webs, so let's say it is D, so D by 2 you will consider half the distance between two webs here, the same on the other side. So D by 2 at least you will consider this is the distance between two webs, adjacent webs of the flange walls. And 1/10 of the total wall height. So total wall height would be from bottom to top. Okay, so h by 10, not small h. So small h is the story height, capital H is the full height of the wall. That is the criteria given. So either I will take B, or I will take 1/2 of the distance between two webs, or I will take h by 10. The minimum of the three will be equal to your B effective. Okay, so that is how you will find the flange width that will participate in the resistance. I hope it is clear now, this important criteria. So in ACI code, it is given a bit separately. 26-degree angle they have considered. 26-degree angle, you will get whatever the width is there, you can use it. But we have this particular requirement, we have to follow this minimum requirement. Now, spatial shear wall shall be provided with uniformly spaced reinforcement. So in ETABS also, you have two options when you are defining the shear wall as a pier element. Now new ETABS is defining it automatically. Previously we had to define this is a pier element, this is a frame element. So pier element will be defined as shell, your frame element defined as your plane elements, 2D elements. So the piers numbering is critical. So each shear wall will have a pier and a spandrel. So spandrel will come in a case that we have a shear wall and there is an opening in between. Okay. So this portion and this portion, both sides will act as a pier. So P1 and P2, and in between this portion, okay, this much area in between will act as a spandrel. So that would be S1 or S2, S3, that way it will act. So the definition of spandrel and pier is also not given in the IS code. You should refer the book of Jack Moyle. So after the session, I will just message what is the size of the spandrel, what is the size of the, how to differentiate between spandrel and pier. If this size is of quite different amount, it can also become a pier. Okay, so how to differentiate between spandrel and pier? Spandrel is a beam connecting the two shear walls, and it will also act as a coupling beam if the opening is that way. So this will be dominated by shear, and the size has been given in the ACI code, but not in our code, that what is a spandrel and what is a pier. But this will act as a pier on two sides. In between it will act as a spandrel, and below also it will act as a pier. So this will be P3. So what we can say is, if it is continuous, then it will become like this, otherwise it will also act as P3 in this much portion. So this is how the this shear wall with openings are defined. So spandrel is there, pier is there. So pier and spandrel, two type of elements, more of a beam, but all are shell. and it acts as a coupling beam. So we have two types. One is the uniform distributed reinforcement. Whatever the reinforcement you are getting, you are distributing it uniformly on both of its faces. So that is the uniform reinforcement as per our IS code. And also ETABS, the case one would be that uniform design as per uniform reinforcement. Second is your C type and T type, also defined in ETABS. That if it is a flange wall, we design it as per the C type and T type. If it is a rectangular, then we define it as a what we say uniform reinforcement. Okay, so
Sir,
our code says that we should have uniform reinforcement on both sides of the wall.
sir, hello.
Yeah.
Sir, I have a question regarding the spandrel and pier. Let us suppose I have a wall and there is a window opening. In the SAP, I am using that just let us suppose my window opening is 1 meter. Okay, I am assigning my wall and I'm just removing one panel, 1 meter panel. Okay, I'm not differentiating anything spandrel or pier or like that in the SAP. But when coming to the EATS apps, there is a problem that we have to define labeling as a spandrel on the top of the window and below window and the sides of the just like what you told. Then sides of the walls you have to define the name as per pier. Sir, why this the softwares differentiate? I mean like this.
So
What will
now new
happen?
software considers it adequately. Don't need to define it.
Sir,
So
I
it
did not get.
takes automatically. New ETABS takes it automatically.
Okay. I mean,
But if you are dividing the shear wall,
right.
people what they do, they don't use the auto meshing, they divide it by themselves. Then you have to define it that this is a spandrel, this is a pier.
Okay.
You are manually breaking the shear wall, right?
Okay. Okay.
Versus the auto mesh.
Right.
If you are manually breaking it, then you have to define it. This much is a pier, this much is a spandrel. Otherwise, if you are using auto meshing, software will take automatically.
Okay. Okay, sir. Okay. But I try to understand this why these concepts came in the ETAPS itself. I mean, what the I'm not understanding that the behavior. Why should I can't provide the same steel on the top of the window also? Why we are assigning the name it's spandrel and we are talking like that? Sir, did you get my point? What I'm trying to ask you?
It's why we are defining it because they are separate.
Right.
So it cannot be continuous because its design will be different. Two
Okay, sir.
elements are different. One is acting like a beam, one is acting like a cantilever.
Okay, but whatever the scenario, the entire panel is being a single unit, na sir.
It
Just
is
to
single
we,
unit, but uh,
just we are removing only one panel of 1 meter element in the wall itself. Let us suppose I have a 4 meter of wall and 3 meter height. So in the 3 meter, I am just puncturing 1 meter.
I think this book is very important for you to refer in this case because it goes with manual analysis and it actually describes that how the coupling beam or the shear wall are considered. Mm, so this is the structural wall section. Okay, that. So
Right, sir.
Sir, what is book name?
I'll share it in the group as well. So this is for the coupled walls. As you say with openings, it is a coupled wall. So clearly, if we follow this, this is a So see, this is the basic arrangement that your beam has been considered like this, and also the floor. So So if you are going by a finite element tool, now this method has two important advantage. It requires a rather simple program. So we had simplified the analysis rather than a FEM software when we had problem in our RAM and all those things. Okay. So FEM software was considering everything, but we have made it simpler by considering its different elements and reducing our computational effort. So we define it as a separate beam element, and we define it as a separate pier element, and we take the effective stiffness and the effective width and try to solve the problem. So these are the rigid beams we are putting at the two ends, so that will act as uh, a coupling beam. So here you can see three columns: column 1, column 2, column 3. Okay, three columns are there, and in between the rigid beams are there. Okay, so this in between these rigid beams, you can see the normal beam as well. So your coupling beam was analyzed like this for simpler analysis rather than the FEM software. So if you are able to use the FEM software, then it can categorize the forces or find the forces as we divide the elements versus your simplified analysis model. So same, you can see two columns are there, what I had drawn, and in between the stiffness modifier, you can see these are the coupled beams. Coupling beams are on the edges. These are the rigid links. So that will act as a your column, and in between it will act as a beam, and it is dominated by shear forces VL and VL. So once you refer it in more detail, you will get exactly that how it was previously working and how it is right now working. So we will get the same type of moment and shear diagram, but in a different order as we are doing it manually compared to the FEM results. I hope I'm able to give you some hint of it, that why we are separating and why it was separated.
Yes, sir.
So
Yes.
SAP was a purely FEM software versus the ETABS. ETABS has grown now. If you use AutoMesh, it will take automatically. You don't have to define it. If you are meshing by yourself, you will have to assign by yourself.
Oh, okay, okay.
Okay, so definition of the spandrel is given in the book of Moyle. So that I'll also share.
Right, sir.
So as I was explaining that uniform reinforcement is what we are considering as per IS13920 for rectangular shear wall, and for a plain shear wall CNT type, the option is there in ETAB, so that we have to design those with this option, and rectangular shear wall as per uniform reinforcement option. Okay, so
Sir,
this
sir, I have a question here also.
let me first continue so
Okay, sir.
I
Okay,
can
right.
end this part. Then at least a minimum area of reinforcement bars is indicated in table 1 shall be provided. So this table gives the minimum reinforcement in the shear wall, and horizontal and vertical reinforcement have been defined here. So for squat walls, minimum is your 0.25%, and vertical minimum is 0.25 plus 0.5, 1 minus height upon thickness of the wall, and whatever the horizontal density of steel you have provided minus the 0.25%. So if you have given minimum here, this will become 0, then vertical also becomes minimum. If it is more than 0.25%, then you will get some additional in the vertical reinforcement. So minimum in both cases is the same, that is 0.25%. And when we are providing the density V net, so that is a vertical reinforcement in the web plus thickness of wall, length of wall minus 0.02 minus 2.5 into whatever the reinforcement is provided in the vertical direction in the web. So what is this net mean? That why is this net provided? Rho V net. And vertical reinforcement provided should be less than the horizontal reinforcement provided because it is shear dominated. That's why it should not govern in flexure. Vertical reinforcement is less than the horizontal reinforcement. But what is this net reinforcement and why it is related to web? That has not been explained in the code. So anybody has understanding on this, because nowhere it is mentioned anywhere that how it is related to web rho v net. Anything?
No, sir, no, we don't know that actually.
Yeah, so nowhere it is mentioned, but if we refer the ACI code, we will be able to find it. So I'll also send with respect to that, or we can also check in the nomenclature section that we have in the beginning. So this is the rho v net minimum. Starts from here only. So minimum area of vertical reinforcement of a structural wall as a fraction of gross area of cross section of the wall. So net reinforcement versus the gross area of the wall. So that is what has been shown when it is showing as rho v minimum. Rho v minimum has not been given the definition. Okay, so rho v be minimum. So minimum area of vertical reinforcement in each boundary element of a structural wall as a fraction of the gross area of the boundary element. So minimum area of horizontal reinforcement as a fraction of the gross area of the section. So net area and gross area, basically it is representing that, but in horizontal they are not mentioning as net, but it has been mentioned as a fraction of the gross cross section. This is for the boundary element minimum. This is the net section to be provided, and this is the net reinforcement to be provided, minimum net reinforcement. And in the web vertical direction, what should be the minimum in the web? So wherever the net and gross is there, that means with respect to the full cross section area, this much is the minimum to be provided. So if we look at it again, horizontal minimum with respect to gross area, rho v minimum with respect to your horizontal is given, but net area has to be satisfied, and your vertical provided should be less than horizontal provided. That is for squat walls. For intermediate walls, it has been given if it is a boundary element is there, then minimum should be 0.8% in the boundary wall vertical reinforcement, and the net reinforcement and in the web should be at least 0.25 vertical reinforcement, and horizontal is also 0.25 with respect to gross area. and vertical net minimum has to be satisfied. So this should be a satisfactory clause, minimum clause for vertical reinforcement with respect to gross area has been given. And if your minimum is 0.25 and 0, sorry, this is given in your 0.25%. As you can see, your net is more than 0.25%. So how can you make it? That is what I'm asking. So rho v net will depend upon the web. Okay, so if it is 0.25 here, 0.25 here, still be more than 0.25, because this will be 0.25 because this will become 0 if your rho h is 0.25. So this becomes 0.25, but this will become higher than 0.25. So your net reinforcement requirement will be higher than 0.25, though it is mentioned as 0.25. So either it would be with respect to your what we say that web and flange, because it is talking about the web. When we are talking about the rectangular wall, there is only the one rectangle we are talking. So there will not be a web. So if it is written as web, then your flange also has to be there. So I think for rectangle, we have to follow only this clause, and if you are following this, then you will have to find a web. If the web is not there, you will not be able to give that reinforcement. Okay. So this is the boundary element. So boundary element will act as a flange, and your no boundary element is there, then it will act as a simple wall. Then there will not be a flange. So web will not come. So when there is a boundary wall, there will be a web, and there will be a flange. So if this is my shear wall, and this is my boundary element, this much portion. So it is acting as a flange. It is acting as a web. So that category now you have for the net vertical reinforcement. Okay, so I hope you understand what is the reason to have this web minimum and V net minimum. So net has to be as per the gross area, which will be more than 0.25%, because thickness and length cannot be 0. Here also, if your row vertical web some reinforcement is given, then it will be definitely more than 0.25%, because minimum is required. So vertical provided, if it is 0.25, horizontal is also 0.25, but it is mentioned it should be less than that. So you cannot provide 0.25 in both cases. I hope you are getting it. Minimum is 0.25 here, then both are equal, but this clause will not satisfy in squat walls. For slender wall, rho h minimum has been given, and rho h minimum is depending upon rho h. So let us check again what is rho h. I think rho h is not mentioned here. So there are some drawbacks, but if you are referring that for
Sir,
slender walls, yeah.
let us suppose if I'm getting a boundary element for the simple rectangle wall,
Hmm.
so I have to design it is as a CNT method, right?
No, it is not a CNT method, but it will act as a flange, but it is not CNT.
But just now you mentioned that CNT will do for the flange shear walls.
No, it is representative of that, but let's say what we say that CNT should be actually CNT type. It should not be rectangle.
Okay, sir, but in
So in
rectangle shear,
rectangle also, if your boundary element is there, that will also act as a flange.
okay. boundary element is also acting play. So it should be designed with the simple uniform reinforcing steel, right?
No, boundary element act as a column, so they are the column design. Web will have uniform reinforcement, but E-tabs you will select it as uniform reinforcement.
Okay, sir. Okay.
Yeah.
Uh,
So anybody can tell me how you consider this rho h minimum formula? As rho h has been mentioned, but nowhere the rho h value has been given. So rho h is your calculated one. Okay, you have calculated as per the forces the percentage of steel required in horizontal direction. Okay, so that you will be putting it here, and from that you will be finding the rho h minimum. Right now, if you have not provided anything, the minimum will be 0.25% if it is not required. Then at least 0.25%. If it is required, then your minimum will also increase with respect to reduction from minimum. So how much minimum is provided, from that addition will be there, rho h minimum. From 0.25% it will increase. So up to squat and up to intermediate 0.25 was the minimum, but for slender it will add. Okay, for shear and bending, both actions it will require. Then row vertical boundary element 0.8%, it is the same. Row vertical in the web minimum, that is boundary element is the column in between the boundary element, 0.25% uniform reinforcement. Row v net minimum has to be also followed. So as per the cross section, this should be the net area in vertical direction that is required. In all cases, you need to check that. It will always be more than 0.25%. Okay. So select your particular case and reinforcement accordingly. Now reinforcement bar shall be provided in two curtains within the cross section of the wall, with each curtain having bars running along vertical and horizontal direction when factored shear stress demand in the wall exceeds 0.25 root FCK or wall thickness is 200 mm or higher. So basically, if we have a rectangular shear wall, the reinforcement should be provided in two layers, two curtains. When your thickness is 200 mm or higher. Okay. And factored shear stress F, let's say, is root of FCK into 0.25. Then you have to provide the reinforcement in double layer. That is what has been mentioned. When steel is provided in two layers, all vertical steel bars shall be contained within the horizontal steel bar. So now we go towards the detailing. Then I'll just draw a small section. So these are your vertical bars. It has to be contained within the horizontal bars. Let me draw the horizontal bars first. So all vertical bars has to be contained within the horizontal bars. So confinement of vertical reinforcement has to be there. Okay, so detailing is very critical in this particular case, how you are doing it. So if there is a boundary element, let's say this is the boundary element, then you will confine it separately like this. So this will act as a column reinforcement or boundary element, and whatever the reinforcement will come from here will go inside this. Okay. And all vertical reinforcements have to be contained within the horizontal reinforcement. So detailing is very critical, with boundary element, without boundary element, how you will detail it, it is very important. So keeping a boundary element, how it helps that your congestion in the, yes sir, you can speak.
Sir, concerning the stirrups, we will discuss about it in our next future. There is some recommendation of in the code concerning the tie and the angle and the length of the end, the stirrups. It should be at least 10 phi with certain distance inside the beam. Otherwise, it will not affect.
So you are talking about this LD.
Yes, at this end beam, yeah, the tie of the stirrups, the hook. Yes, this one.
Okay.
There is some specification in the ACI. What should be the distance inside the beam and what will be the angle of this one?
So it is 135 degree as per the
Yes,
IS, as per
with
the,
10 5 inside the dead beam,
yes,
the
10,
length of
10.
this.
Yeah, so it is same in IS code also, and
Yes,
we are following as per the columns, the ductile detailing. So the ductile detailing will be same as we do for columns for the boundary element.
yes,
So the
that's it.
spacing would be maximum, so minimum 100 center to center of the stirrups, 135 degree angle of the bend, and it has to have that adequate diameter, and uh, the third part is related to whether it is required throughout the length of the column or not. So at what length this spatial ductiling reinforcement has to be provided. So section 8 has that in the IS code. So it is similar to ACI code as well. So the
Yes,
ductile
the
detailing,
minimum should be 8. The
yeah,
section minimum
minimum
should be 8.
minimum is 8 yes,
8 millimeter.
yeah, 8 mm minimum. That same has been
In
mentioned
the
in,
Turkey, in the Turkey earthquake, we observe a lot of problems due to the less than, they use sometimes less than 80 millimeter, 6 millimeter, and the hook will explode. So there is no hook because 6 millimeter with tie element, there is no work for it.
so actually we are using HYSD bars. We are not using mild steel bars. So in HYSD you cannot have 6 mm. So minimum we get is 8 mm in
We will
HYSD.
discuss about also
Yeah,
the
sure.
the percentage of carbon in the
Yeah,
rebars,
yes,
because sometimes we mention the existence of bar as coated, there is no ductility,
yes, yes.
suddenly
Okay.
broken.
Yes, yes, yes. So in here also in Puja earthquake, we the report also mentioned some of these points which are very important to discuss. So we will discuss that point on 21st, on which we have, that is the next Sunday, we have kept the session. Yeah, thank you.
Sir, will you kindly throw some light on the uniform reinforcing steel and CNT methodology? What is the basic design philosophy of those two methodologies?
Yeah, let me finish this part. I'll just focus on that. As I had already informed you, what is the effective area in which the reinforcement has to be there. In a rectangle, everything is uniform versus the flange, only that much portion where the reinforcement density is required. There we provided, rest is the minimum steel. So the distribution of steel changes, not uniform in CNT as compared to rectangle. And the benefit of using foundry element is that you can use minimum steel in the web. Okay, so your congestion is less, so your element after concrete is better, so you don't have the feel the congestion of reinforcement. Otherwise, throughout the height of the building, the reinforcement congestion you may experience. So in US, what Jack Moyle has mentioned in his reference book, that they follow to have boundary element, and this boundary element is having high density of ductile reinforcement. Here it is just minimum steel is provided, minimum versus higher ductile reinforcement in this. So congestion is more in this portion only, and you get a good enough length where the congestion can be avoided. So that way they are doing the detailing or selecting the type of the wall to be provided. I hope it is clear step by step. So that also we will see.
Yeah, okay,
So
sir.
so your horizontal bar should enclose the vertical bars. The largest diameter of the longitudinal steel bar used shall not exceed 1 by 10 of the thickness of that part. So if thickness is 200, you cannot use more than 20 dia bar. So 1 by 10 of the thickness, the largest diameter of the longitudinal bar shall not exceed 1 by 10 of the thickness of the wall. So maximum spacing of vertical or horizontal reinforcement shall not exceed smaller of. So what is the spacing of vertical or horizontal reinforcement? So either it is vertical, whether it is horizontal, it should not exceed 1 by 5 the length of the wall in horizontal direction, 3 times the thickness of the web of the wall, and 450 mm. So spacing cannot be more than the 3 criteria mentioned here. Whatever is the smaller, you have to take from the 3, and your vertical and horizontal spacing has to be detailed accordingly. Now, spatial shear walls shall be founded on properly designed foundations and shall not be discontinued to rest on beams, columns, or inclined members. That means it is saying that we cannot have a transfer girder, and it cannot rest on a column, neither any inclined member, and it should be continuous from top to bottom, that is top of the raft. Discontinuity of shear wall may be rejected, or any failure of the structure therefrom will be against the law in this particular case. So
Even though
transfer
it,
girder are not recommended in this particular case for spatial structural walls.
sir, even though it is transfer slab also is not recommended, right?
Even the
Transfer
transverse
slab.
transfer girder, no?
Yes, sir. Yes, sir. I mean, not a gutter, transfer slab, not a transfer beam system, transfer slab system.
No, shear wall cannot be on a slab, no? I have never seen that.
No, no, sir. Transfer slab is a depth of around 1.8, 2 meter like that, no, sir.
That is transfer girder only.
Okay, okay.
So that is not recommended basically. They provide full floor height also, the beams. So that has been used at many places. They provide full height of the floor as a beam on which they support the columns or shear wall. So for columns, you can say that that is also not recommended. For shear wall also not recommended as per the code. So that was about basic of the shear walls, mm, detailing and all those aspects. And design for shear force, as we know how to find the stress, whether the shear reinforcement is required or not. We have shear force. Now factored shear force is for the full height of the building. Then thickness of the wall and depth of the wall. Now effective depth of the wall section, uh, which may be taken as 0.8 times the length of the wall for rectangular section. So if you are using rectangular section, 0.8 times the length will come in dW. So you get a shear stress, nominal shear stress demand on the wall, and the design shear strength tau c that can maximum be available with a concrete section as per table 19 of IS 456 2000 as per the grade of concrete. If your tau v is less than tau c, okay, let's say it has been mentioned when nominal shear stress demand tau v on a wall is more than maximum design shear strength tau c max of concrete, the wall has to be redesigned because you cannot go beyond this capacity. So you need to redesign the wall. If it is less than tau c max, so that is uh, your tau v is less than tau c max but greater than tau c, then your horizontal reinforcement is required. So you don't have to redesign it, but you have to provide the additional reinforcement to take care for the shear stress demand higher than tau c. So how much that reinforcement is there, that you can find from here, that is ultimate minus concrete tau c. So the capacity of concrete we are deducting from ultimate, so we get the PUS, that is the shear force required for the steel. So from ultimate shear minus the tau c into thickness of the wall, depth of the wall. So tau c is defined as per the grade of concrete in the code. From that you can get VUS, for which the reinforcement has to be provided. So VUS upon 0.85 Fy D upon SV is the spacing of the vertical stirrups that you get from 10.1.9, and from that you have to provide the horizontal steel. The minimum area is given in this particular table. Now your tau v is less than tau c. Horizontal reinforcement shall be the minimum area as provided in the table. So tau v less than tau c, then minimum steel as per table 1. Tau v is greater than tau c, then you reduce the shear capacity of concrete, find for the steel, find the horizontal steel area, and it should be greater than or equal to the minimum steel in table 1. Is tau v is less than tau c, then minimum steel has to be provided for the shear forces. So this is how we find the area of steel and then percentage of steel. The next part is related to axial force and bending moment. So every shear wall has a PMM interaction curve. So PM1 and PM2. Okay, interaction curve you will get from the software. Same you can also make your PMM interaction curve if you want for the rectangular shear wall. And development of those PMM interaction curves require a formula and neutral axis depth. So based on that you have to develop the PMM interaction curve, and you can compare it with the software. There is a P wall software is there, in which they have given the calculation that how you can find it. So I'll share in the group that how they have done it in P wall is a separate software that is based on ACI code for design of the shear wall, and you can compare the both results of the two, E-tabs and the P wall. P wall is purely finite element based software. So PMM interaction curve is required for any shear wall, especially if it is a slender wall. The moment of resistance of a slender rectangular structural wall, that is rectangle in nature, can be found in annexure A. You can find the XU limit XU, and based on that you can find the capacity of the wall for the moment. Okay. So expressions given in Exercise A are not applicable for structural walls with boundary elements. So if there are boundary elements, you cannot use them. You will have to refer the book of Moyle for this. So the cracked flexural strength of a wall section shall be greater than its uncracked flexural strength. So why this clause has been mentioned? Any reason for that? Correct strength should be more than uncorrect strength. I don't think anybody would have checked for this any place.
No, sir, no, we did not check this also.
If
But
it is
generally, it's not possible also, na, sir.
no, if it is not possible, they would not have mentioned. So let us see 10.3.2. If in amendment they have changed. It is 10.3.2. So here in this clause you can see LW has to be substituted for TW in the formula for rho V minimum and rho V web for rho H in the formula for rho H minimum. So there was some problem in the formula. You can see rho V web for rho H in the rho H minimum formula. It was mentioned. So you just refer the amendment also for that formula. 10.3.2 is not changed. Again, let us see. So ordinary RC structural wall, also called shear wall. In the beginning, let's say. So spatial shear wall, that is spatial RC structural wall, ordinary RC structural wall is a shear wall. So wherever you are mentioning it shear wall, it is ordinary. Where it is spatial shear walls, you will be having spatial RC structural walls. So 10.3.2. So no change, that means it is consistent. So cracked flexural strength has to be more than the uncracked flexural strength, because as your stress will increase with respect to strain. So when it is uncracked, okay, the strain is less. As it is going towards the crack, the strain will keep on increasing. So when strain is increasing, your stress will keep on increasing. So your internal stress is higher. That means your internal resistance is higher, right? So if we reach 0.0035 for the concrete stress, that means it is the ultimate strain that we are facing. And with respect to the generated strain, the stress will get developed and it will be higher for cracked section as compared to uncracked section. So this is the reading between the lines that I could see, but it is not yet confirmed by anyone in the code. Okay. So in the structural walls that do not have boundary elements, at least a minimum of 4 bars of 12 diameter arranged in 2 layers shall be concentrated at as vertical reinforcement ends of the wall over a length not exceeding twice the thickness of the RC wall. So their recommendation even for this uniform reinforcement is at least 4 bars has to be placed at the edges for a width of 2 times the thickness and rest can be uniformly placed. So even if the boundary element is not there, for 2 times the thickness of the wall, 4 bars has to be provided. Though it is not having any horizontal stirrups like for the boundary element. When it is a boundary element, it has to be enclosed with the stirrups like for the column. So that is for the shear wall. Now that is a boundary element. So what I was thinking that I think we have discussed too much for today. If you want, I can continue, but it should not get all jumbled up for you. So should we continue or should we have a break and continue it in a separate session? Hello.
Yeah, sir. It's yeah. We can take a break. All the other opinion.
I mean, I can continue, but do you want me to continue and complete this much part? Because boundary element I will continue, then it will end, I think. So let me continue the code at least. The rest that model generation and all, I'll share it in a separate video. And also the inferences from that book I'll share with you. Okay, so let me
Sir,
complete these 2 parts. Yeah.
do you like to share the small video as a break?
Yeah, sure. Yes.
Okay.
Yes.
Can you see it?
We can see video and media 2 folder is there.
Ah, it's still there. I'm gonna try each time to share it. I don't know what happened. Even that.
You want me to share that 8-second video is what you have uploaded
Yes,
in one
if you
of the
like,
group.
if you can, it's more better. I don't know what's happened because I'm trying to work it, but I don't know why.
Okay, let me just. Is it visible to all?
Yes, it's visible for me. Thanks.
So you
So,
want me to start this video, right?
yes, please. In the background of this figure, we can see that there is more than buildings and tall buildings. Those buildings still at the same with the small cracks, with the broken glass, but we can see that I have buildings almost 5 to 6 floors. They are totally destroyed. So in the same zone, for the same earthquake, for the same magnitude, almost the same soil, a tall building resists, however, small building destroyed. We will think about this point. Please, let's start this video. Those are the main parts. We will discuss, please stop it. We will discuss about the P delta effect and we will discuss about, mm, it's so quick. Can you back please? Okay, stop it here please. In this figure, in the background of this figure, one of the column exists. We found a plastic bottle of water inside the concrete. Of course, this bottle will not cause to damage, but however, we will think about the construction phase. There is no meaning to have a full-scale drawing, a wonderful design, and a very bad execution. You can see the stirrups in the slide, how they have small concrete cover and the cracks. Yes, there is almost neglected. So when we have small cover concrete, so we should think about the corrosion that will happen to these stirrups. Please, the next one. Okay, this building, as I told you before, one my friend told me like someone push it from the top. There is a small gap. This for 1 point something meter. At the base, the building still erect. However, it's tilt. This is the P delta effect and how should resist it. The next one, please. Yes, please. We will think about the composite section and how should reduce the punching shear effect because in many area we can see the rebars go deeply inside the slabs. So we should think about the punching shear and the non-conventional reinforcement because as a conventional reinforcement, normal, the stirrups, the ACI code recommends the stud types, but we have used as a reinforcement, we have a patent about hairpin shaped reinforcement or inverted U. Yes, this one. This one show by several experimental and numerical modeling that it could be resist more and have bigger development to confine the concrete inside it in the localized zone where we have a maximum stresses. Next, please. Yes, concerning the non-structural element, we should think about how to assure life safety without much property losses
మీ
and still have
షుగర్
functional
చేసుకునే
losses.
యాప్ పేరు ఏంటి ఇలా పెట్టి చెక్ చేసుకుని
Because when we talk about
ఇలా పెట్టి
deaths
చెక్
or
చేసుకుంటావు కదా
dollars or continuity,
అది
we
కాదు
should
తెల్లది
think about what we can assure for the people, how to reduce this risk. Hope that we next session have better discussion about each part, how to save our life and the life of the others. We can use additional reference like National Center for Seismology, LCS, or the FEMA, which is the code required by ICKI code.
Okay, so I think all have got the basic understanding. We will also circulate the brochures with highlight points that what aspects we are going to cover next week, and for that we will share the brochure in the group.
Hope to see you next week and
Yeah.
join you in a special topic.
Yes, yes, sure.
Any question, they can send it on the group and we can prepare
Yeah,
it for
as I
next
share
session.
it in multiple platforms, let us have a
Yes,
separate discussion for that. If the queries are there, we'll resolve it in that particular way.
yes, thank you.
Thank you. Okay, so highlight for the next week, and let us continue. That is boundary elements. Now, in what case the software also finds the boundary elements is that when the stress, extreme fiber stress exceeds zero point 0.2 FCK, in that particular case, the software calculates the capacity and provides the boundary element for the required additional stress. If it is more than 0.25 FCK, then it will calculate what part of the wall will behave as a boundary element. And accordingly, we have to detail it and provide the boundary element as a column and follow section 8. in which the column depth detailing has been mentioned, and it will also have a same PMM interaction curve as of a column. So it will behave as a column and designed as a column, and in between the boundary wall it will act as a rectangular web of the shear wall. And the based on that you have to provide the nominal steel or what is required generated the forces. Based on that we provide the reinforcement that way. Okay, so if a boundary element is taking most of your forces, then the web will have minimum steel. And boundary elements can be discontinued in elevation when the stresses extreme fiber stress goes below 0.15 FCK. So you can discontinue the boundary element after that level. And extreme fiber stress should be calculated in elastic model and using the gross section properties specifically mentioned here. So in this they are asking for gross properties of the section and an elastic model. A boundary element shall have a adequate axial load carrying capacity, assuming it as a compression element of a short column action, because short column action will come in your story wise, so as enable it to carry axial compression arising from factored gravity load and lateral seismic shaking effects floor wise. Okay. The load factor for gravity load shall be taken as 0.8 if gravity load gives higher axial compressive strength of the boundary element. So if it is actually producing a positive effect and helps in resisting the moment, the axial forces, then you can consider 0.8 times the gravity force, not the full gravity force. In that particular case, if the building is very heavy size, giving very high amount of protection to the boundary element, then you can take the gravity forces as 0.8, not full gravity forces. Requirement is same as for the column. In the boundary element, 0.8% steel, minimum 0.8 to 6%, and 4% to avoid congestion in the boundary element should be provided as vertical reinforcement. Boundary elements where required as per this shall be provided with special confining reinforcement throughout their height. So throughout the height you need to provide your special confining reinforcement as defined in section 8 for stirrups of circle or rectangle. It is 0.05 SV, that is the vertical spacing, height, that is the depth of the boundary element, FCK upon Fy. So you will get a horizontal stirrups. The spacing should not be more than 1/3 of the minimum member dimension of the boundary element, that is the width, the thickness of the wall will be the minimum in this particular case if it is rectangle. So 1/3 of the minimum member dimension of the boundary element, which will be thickness B or T, 6 times the diameter of the smallest longitudinal reinforcement bar. So if it is 12 dia, then it is 72 720 mm. So 6 times the diameter of the 72 mm. Okay, 6 times diameter of the smallest longitudinal reinforcement bars, that has not more than, okay, this is the minimum requirement, 100 mm but not, and may be relaxed to 150 mm if the maximum distance between cross ties or parallel leg of links or ties is limited to 200 mm. So you cannot go below 100 mm, you cannot go more than what we say that 1/3 of minimum member dimension and 6 times the longitudinal bar. And you can keep minimum as 150 mm spacing if the ties that you provide are at spacing of 200 mm, is limited to that, Then also you can relax your spacing in the vertical direction to be 150 mm instead of 100 mm. So you cannot go below 100 mm or 150 mm in this particular case. So but need not be less than 100 mm as specified here. Boundary elements need not be provided if the entire wall section is provided with special confining reinforcement as per section number 8. So this will be very dense reinforcement and difficult to do concreting. That is the reason boundary element are provided as recommended by the some of the experts. And if full wall is acting as a ductile wall and special confining reinforcement, then it has to follow your regulation as per section 8 of this code. So that was related to this of boundary element. And where boundary element is not required, that means full wall is ductile detailed as per section 8, which will complicate your concreting. So as previously understood, coupling beams are coplanar spatial structural walls, may be connected by means of the coupling beams, which are shear dominated deep beams. If earthquake induced shear stress in coupling beam exceeds 0.1 FCK LS upon D, LS is the clear span of coupling beam, D is the overall depth, the entire earthquake induced shear, bending moment and axial compression shall be resisted by diagonal reinforcement alone. So if earthquake induced shear stress in coupling beam is exceeding this much part, the entire earthquake induced shear, bending moment and axial compression. So this is only we are talking about the lateral force, no gravity force. It has to be resisted by moment and axial compression has to be resisted by shear, moment and compression, resisted by diagonal reinforcement only. If the stress is exceeding this limit. Okay, so that has been clearly specified how you need to design it. Now area of this diagonal reinforcement along each diagonal shall be estimated as total shear force upon 1.74 Fy into sine alpha. Alpha is the angle of the diagonal, and that would be the area of the steel that is to be provided in diagonal direction. That's why it is ASD, in diagonal direction. And at least 4 bars of 8 mm diameter shall be provided along each diagonal. So it would be something like this. If you see that diagonal 4 bars with specially confined reinforcement has to be provided along the diagonal like this. Okay, so minimum 4 bars of 8 mm diameter. That is the minimum requirement. And this is special ductile detailing. All longitudinal bars along each diagonal shall be enclosed by special confining transverse reinforcement as per section number 8 at a spacing not exceeding 100 mm. So this spacing should not be more than 100 mm. Okay, it is specially ductile as per section number 8 of ductile detailing for the beams that we are doing. The diagonal of a coupling beam shall be anchored in the adjacent walls with an anchorage length of 1.5 times the development length in tension. See figure 16. So what would be the anchorage length? 1.5 times the development length, that is the LD. So that much reinforcement has to be extended in the shear walls, 1.5 times the LD, development length. So I think coupling beam, how to design it is a separate case, but how to consider it, that has been mentioned here. If it is fully resisting the force due to the earthquake, the stress is higher, then we need to follow this formula and provide the steel. So we use the factored shear force on the coupling beam, not the total shear coming from the earthquake. Factored shear force on the coupling beam and the angle made by the diagonal reinforcement with the horizontal. So what force is coming on the this coupling beam, that shear force has to be considered due to the earthquake only. Okay. So shear strength of a wall with openings should be checked at critical horizontal planes passing through openings. Additional steel reinforcement shall be provided along all four edges of opening in wall. So this is very simple. Only thing is, if there is a opening in the shear wall like this, so how much area of steel that you have cut, it has to be provided in your two directions, 50% on both sides. Okay. The area of these vertical and horizontal steel should be equal to that of the respective interrupted bars provided, half on either side of the wall in each direction. So this is for vertical. Same horizontal that you missed or cut 50% it's to be distributed along this perimeter like we do for any other opening. That way this opening has the reinforcement has to be detailed for the shear wall openings as well. These vertical bars should extend for full height of the story in which the opening is present. So the important part is, if this is the one story, then for entire story, let me draw it properly. So it should go something like this for the full story. Horizontal direction, you should have that development length. So 50% of vertical on both sides, 50% of horizontal on top and bottom. This way the opening of the shear wall has to be detailed story wise. The horizontal bar should be provided with development length in tension beyond the edge of the opening. So this will be have LD. So this was regarding to the rectangular walls. Now we go to the capacity for rectangular shear wall. So first we find out the neutral axis of the wall, phi plus lambda to phi plus 0.36. Now what is the phi? It is given 0.87 Fy into density of steel upon Fck. Lambda is related to the axial force, Fck, thickness of the wall, length of the wall. And your steel is given by AST upon thickness, length of the wall. So AST would be area of uniformly distributed vertical reinforcement. Okay. So from EST you will get the density of steel, you will get PU, from that you will get phi and lambda, so steel and PU forces. From that you will get your XU through LW, you will get XU limit, the same formula we use for the beams, that is XU limit, and based on that XU less than XU limit, XU greater than XU limit but less than 1. So two cases have been given, and mu upon FCK TW LW square. Again you check the amendments, whatever the changes are mentioned in this particular formula. If some changes are mentioned, amendment number 1 to section A1. I think there is no change in this particular case, but in the minimum reinforcement formula there is some change that needs to be marked. Okay. So from that you will get your moment based on phi and lambda, XU upon LW, beta square by 3, and this beta is given here, that is 0.002 plus 0.87 Fy upon here, 0.0035, that is inverse of your this much part. Okay, so that is your beta. So from that you can find the moment capacity of the wall in case A, moment capacity of the wall in case B. Here the what you can see, a algebraic equation has been given in form of alpha if your XU is greater than XU limit but less than 1. So what XU by L you need to use, you need to solve this equation and find XU by L, that is the algebraic equation. So your alpha 4 and alpha 5, so alpha 1, 2, 3, 4, 5 has been given. So that are related to phi and beta. So you can find a XU by L solution and use it in this equation to find the ultimate moment for the rectangular slender shear wall. Okay, so that was it for a shear wall design as per IS13920. I will add more in the group for the plain shear wall, how it is detailed, and what is the definition of spandrel. Also I'll share in the group. So that was it for today. So if any queries there, you can write in the group. I'll respond to that. So we can close the session today. If any quick doubt is there, I can answer. Okay. So thank you for joining. We will have a next session, special session on next Sunday, and I'll upload the video for shear wall design in the YouTube channel. Okay, thank you.
Thank you, sir.